All right. Hey, everyone. Welcome to the first lecture for summer linear algebra. So we're just going to dive right in. Just keep in mind that these lecture videos are meant to go side by side with reading in the textbook. So we'll progress a little bit quickly through some of these topics, but just as long as you're following along in your textbook, hopefully this is a good pace for us to be at. So what is linear algebra? I mean, just briefly, linear algebra is the study of vectors, matrices, systems of linear equations, and vector spaces. These types of things show up all the time in fields like engineering, computer science, physics, really anywhere that you have to model things that happen in more than one dimension. Um, and so, yeah, many of you have already had the unfortunate experience of having to deal with the components of a force vector in physics, for example, or array lists if you're loving computer science, that kind of thing. These are all uh, things that involve vectors, and so for us in mathematics, we're going to generalize these notions. So let me just maybe write something. Generalize notions of lists of numbers, components, force vectors with components in the forces in the x and the y directions and stuff like that. This is the idea of what we're going to talk about. Again, vectors are the main object of study. Okay, they're the first main object of study. We're going to take vectors, learn how they work, what are they, of course, how do they work, and then we'll generalize them, or we'll generalize those types of notions into more sophisticated objects that we can use to do some really cool applications. But it starts with what is a vector. So a vector has two different perspectives that are afforded. We'll talk about both. Number one is that a vector is like a directed line segment. So specifically, let's look at just some Cartesian plane, with your x and y coordinates. And suppose you have 2 points, A and B. Then the arrow of displacement from A to B, written kind of like this, AB with an arrow on top. This is a vector, and like I just said, it represents, it measures the displacement from A to B, 2 points in the plane. Usually we write this with like a lowercase letter. I'll call it V for vector because I'm not very creative. And the idea behind, okay, I've written these little arrows on the top. Most of the time in a textbook or just out in the world, when you see vectors, they like to write it with like bold font, as opposed to like normal font. Now, that's not really, I mean, I guess I can do it on an iPad, but that's not really doable. Like try that with a pencil, you'll break the tip every time, right? And so we use this notation with the vector with a little arrow on top. Now, another option that you might try is if you have like a half arrow on top. This is for people who don't have time to write an entire arrow over their letter. And if you prefer how this notation looks, you're welcome to use it. I will be using this one for this video, or I guess for our entire class, huh? Okay, and this is all there is to the geometric idea of a vector, right? It is the displacement from one point to another. Notice the order of the 2 points does matter. If you were to displace from B to A, then you would the arrow would be pointing in the opposite direction, but it would have the same length. Okay. Some terminology, the beginning of the arrow, we call it the tail. And the end of the arrow, we call it the tip or head. Okay. The point A, we usually call the initial point. And the point B, we call the terminal point. And I just want to say something quickly about why these words matter. Essentially, in mathematics, we're especially starting here in linear algebra, but moving forward, we care about stating things with absolute, unequivocal precision. In other words, I don't want to mince words about like, oh, like it's the end. That's not really helpful, right? Especially when writing a mathematical proof. We want to show with pure logic and perfectly well-defined terms that one mathematical statement follows from another one. And so, for example, we say that in this geometric view, a vector is the displacement between 2 points, A and B, where A is the initial point and B is the terminal point, right? There's no way to flip the order of those two once we give them names, and so on. It also helps us reference those points in a hurry if we need to. That's enough about the geometric view. This is very common in physics. Much more to the computer science side is the algebraic view of a vector, and it is quite simply an ordered list of numbers. In our case, we'll be working with real numbers, so we can put the word real in here. But in general, in fact, you can have ordered lists of all kinds of things. It depends on, depends on what field we're working with. So if you like the field of real numbers, that's great. You can use complex numbers if you like. You can use rational numbers, and there's more. There's more kinds of options. It's just a question of like what numbers are we allowed to put inside of our vectors. Let me write down an example of a vector for you. Again, I'm going to call it V because V for vector, and I'm not very creative. V might be the vector 1, 3, 7. Okay. Notice this is different from 1, 7, 3, and because the order of these numbers matters. If I were to draw in the geometric view what this vector is corresponding to, it's actually corresponding to, in the geometric view, I've chosen 3 entries. Let's start with 2 for now. I don't want to jump the gun. So the ordered pair, 1, 3. Okay, in the plane, that corresponds to 1 step in the x direction and 3 steps in the y direction. So it will be this vector here. Why did I start at the origin? If in the geometric view, displacement is, we're displacing from one point to another one, I could have started anywhere, gone over 1 and up 3. That's true, and we'll talk about that in just a moment. But for now, this is actually not the focus of what we're looking at right now. We care only about the fact that it's a list of numbers, of 2 numbers specifically. The entries, the first and the second number themselves, these are called components. I will be using that word a lot. Okay. Now I want to write down some things that are going to look really, really unnecessarily confusing. What if I wrote my vector like this? Stacked vertically rather than horizontally. We're going to call these guys the same. Same vector, written very differently. Now, I won't tell you why you might want to do such a terrible thing, but at least not yet. But let's just say that it's going to make computations in the near future way, way easier. Like to the point where it would be inefficient and unnecessary to commit ourselves to using just row vectors or just column vectors. But this is called a row vector. This is called a column vector. And you probably have a preference at the moment. My suggestion is whenever you're going to solve a problem, use the one that you are currently the least comfortable with. For most of you, I would imagine that's this one, column vector. Your goal as an aspiring linear algebraist is to be perfectly fluent going back and forth between both interpretations, either a row or a column. However, it's kind of difficult to avoid having some slight bias. So use the one that you are least comfortable with because you will need both in this class. Okay. I currently have a slight bias towards column vectors, but that's because I committed to using column vectors for this video. And for the rest of this video, I should say it now, I will be using column vectors. The book uses almost exclusively row vectors. Now you'll have the opportunity to see both perspectives. But keep in mind that it doesn't matter if you stack it vertically or horizontally. They represent the same vector. Yeah. Okay. Another point on notation. Seems unnecessary how many times we're talking about notation. You can use parentheses or brackets. The book uses exclusively brackets, which is really sad because I personally use exclusively parentheses. I'm not going to break that habit for this class. So these are pretty much the only bracket vectors that you'll see me draw. I'll be using parentheses. So this is the same as the column vector 1, 3, like this. This is what it is. Again, the reason I like parentheses, they look cleaner. They look a little bit more, a little bit less robotic, we'll say. And also, well, this is the primary reason. Looks better. I encourage you to, as part of the process of making the subject your own, choose a notation that you like. Okay. And yeah, and then commit to it, that kind of thing. All right, so before we talk about how vectors work, I just want to point out a few strange situations when it comes with vectors. So the first one is the zero vector. The zero vector, we write it like this with a hat on the top or an arrow on the top, just a 0 with an arrow. It is the vector 0, 0. No surprise there. Now I have a question for you. How do we draw this 0 vector? Well, start with a coordinate axis, of course. I don't know where else we would start. Initial point, we'll put it anywhere. Might as well put it at the origin. Terminal point, well, 0, 0. We're gonna have to not go anywhere. And in general, this is if a vector measures displacement, the 0 vector represents 0 displacement. So the initial and terminal point are the same. Okay. The 0 vector is very important. It satisfies some properties that other vectors don't satisfy, but it is an honest vector. It is weird. I mean, just like 0 is an honest number, right? The additive identity. You add 0 to anything, doesn't change the value. Well, here, 0 vector satisfies some similar properties. We will come back to this. Well, it'll show up. Okay, R2. What is this fancy R that I've drawn? So this is a shorthand notation for the set of vectors that have two real components. Okay, it's pronounced R2, and if you just walk up to a mathematician and says and say to them, give me an example of a vector in R2, they'll know exactly what you mean. And they'll probably do something like this. They'll probably tell you 0, 0 if you ask a mathematician. But okay, some examples. Besides 0, 0. 1, 1. Okay. How about negative 2.47? Or how about pi to the e to the pi? Yeah, two real numbers. Okay, just stack them on top of each other. You could write them as row vectors or column vectors with brackets or parentheses. Doesn't matter. Okay, the set of vectors with two real components. So ordered pairs of real numbers. Okay. Now, I can think of another structure that we are already very familiar with that collects all ordered pairs of real numbers, namely the Cartesian plane. Yeah? Vector equality, we'll talk about in just a moment. Well, we might as well address it now. The Cartesian plane is the collection of pairs, ordered pairs of numbers. So you would think that this R2 is the symbol for the Cartesian plane. Actually, it is, and there's a very neat correspondence that we'll talk about in just a moment. But first, in order to tell you that, I need to tell you what it means for two vectors to be equal. Two vectors are equal. I'll just say, yeah, two vectors are equal. You might think when the first component is equal to this, their components match up. So like 1, 1 equals 1, 1, but does not equal 1, 2, or 3, 3, or something like that. That's true. But that's you're thinking from the algebraic viewpoint when you consider that. What about these two vectors? Let's see if I can. Oh, look at this. How about these two vectors? Same direction, same magnitude, different initial and terminal points. Are they the same vector? By definition, two vectors are equal when they have the same direction and magnitude. Same direction and magnitude. Okay, so under that definition, these two vectors are the same, as well as any matching ordered list of numbers. Okay, so for that reason, okay, that seems to knock down the number of vectors available to us. You just have the only way to tell them apart is what direction they're facing and how long is the arrow. Magnitude is like length of the arrow. Okay, in standard position, I'll give you a definition and then we'll talk about the correspondence. So a vector is in standard position if its initial point is the origin. And now, what we'll talk about is, let's just consider some vector, 1, 2. Now, in the plane, that corresponds to the point, well, the vector, starting at the origin, going over 1 and up 2. like this. Now, I can make the tip of that vector show up anywhere in the plane just by moving the whole vector. And it is the same vector. However, as soon as I do that, the vector is no longer in standard position. To be in standard position, its initial point must be at the origin. When you force that requirement, that one requirement that the initial point is the origin, now you have a one-to-one correspondence between any point in the plane and any terminal point of a vector. And every terminal point, every point in the plane will pick out a different vector, because what point am I going to pick that's going to preserve the direction and magnitude of this vector over here? There's only one. It can only be the point 1, 2. If I pick a different point, I will have to change either my direction or my magnitude, right? And so this is the connection between the geometric and the algebraic viewpoint, is that we always try to write our vectors in standard position. Almost always. There is precedent for appealing to the geometric intuition of being able to move a vector around without changing its identity. And we'll talk about that now, I guess. Before we talk about that, though, I want to tell you, just we're at a very we're going to change gears a little bit here. So up until now, we're talking about what is linear algebra, what is, what are vectors, whatever. Now I want to start talking about how vectors behave. Okay, and so we will. This is going to have a different feel for it. So if a vector is all about measuring the displacement from one point to another, then adding two vectors together should represent some kind of physical process about having some displacement between 2 points and then doing displacement from where you ended to some other point. Okay, so what we're going to do is take these two vectors u and v. Let's add them together. We're writing them in standard position, of course. When I do, there are different techniques that I can employ. I want to talk about my favorite one. We call it tip to tail. And the idea is take one of your vectors and move it from where it is to some new location where the initial point of the second is the terminal point of the first. When you do, you've created a new vector. The terminal point of the composite of the two vectors is now some other new point that's apparently not even related to the other two, except that it's more like we're doing these displacements in sequence. So this new vector u plus v, it's a vector, and its terminal point is the thing that you get when you geometrically follow u and then follow v, starting from where you ended at u. Notice that notion of adding two vectors commutes. I could have done v first and then u, or u first and then v. Both of them got me to the same location, just we took different paths to get there. And you could think of this as a literal, imagine a hiker in the woods takes two different, this is a true story actually. So I went on a men's retreat last year sometime down to Mount Scott. It's by Lawton, Oklahoma. We decided we were going to climb a mountain, just off-road, and we're just going to go for it. Okay, we went. Let's just say we didn't take the most direct route to get to the peak of this mountain. At every step, we're just that way seems easier, this way seems easier. Very crooked route to get to the top. So we added a bunch of position vectors, something like this, until we got to the top. And from the top, we were able to see the cars that we parked in the middle of a field randomly. True story. Can't believe we survived this. Okay. Notice that from the top of the mountain, it's very easy to see directly what path we should be taking to take the most efficient route back to the car. Now, that was convenient, because we're kind of running out of daylight by the time we got to the top, and we almost turned back because you don't want to be making your way down the mountain in the dark and so on. So, but anyway, we managed. Since we were able to see the top or see the cars from the top, we were able to plot a much more direct route back. This is exactly the intuition behind vector addition. Now that is a very geometric viewpoint. There is an algebraic way of doing this, and the algebraic way is equally natural. Now, let's just, okay, pretend you were inventing linear algebra for a second, and you are an algebraist. You prefer lists of numbers, and you don't like to confine yourself to the geometry. I don't know. Okay. You like the purity of algebra. I've heard that before. Okay. Suppose you wanted to do this then, u plus v, and you want to make sense of it. You would probably, all of you watching this, would probably do the same thing. You would say, okay, well, that's just 3, 1 plus negative 2, 2. There's no magic here, right? If you're going to do something natural, though, you're probably going to, okay, I need one vector when I'm done. So let's add 3 and negative 2, and we'll add 1 and 2. When we do, we get the vector 1, 3. Oh, plus. There's a plus there. We get the vector 1, 3. And sure enough, that point, the terminal point of the purple vector, is exactly the point in the Cartesian plane, 1, 3. In other words, the geometric and algebraic intuitions line up perfectly. We should write that as a definition before we get any further. So in general, let u be this vector with components u1 and u2, v be the vector with components v1 and v2. We define the sum u plus v to be just the sum of the components. So in other words, you add up u1 plus v1 and u2 plus v2. This is a vector in R2, namely, here's the first real number, here's the second real number. It's an ordered pair of numbers, and it's exactly the one that we wanted, right? Okay. Tip to tail, we already saw. There's another way of thinking about this, which is that if you view this shape, oh, that's not good. If you view this shape as a parallelogram, parallelogram, you get the idea. 3 of the vertices, so we're looking at a parallelogram who's with one of the vertices at the origin, 2 of the other vertices at the terminal points of the vectors u and v. What is the meaning of the fourth vertex in this parallelogram? That fourth vertex is precisely the sum of u and v. So it's another geometric viewpoint. Very convenient. But I prefer tip to tail. That's the tip to tail, or of course the component wise sum. Okay. Right, like the algebraic view. Okay. So that's how vectors add. Let's talk about how they multiply real quick. That was misleading. We shouldn't talk about how 2 vectors multiply together. We will define some kind of notion like that in section 1.2, so the next video. But for now, we're going to talk about a more natural definition of multiplication. So think about multiplying 2 numbers. If I were to do 4 times 5, or just, any 2 numbers, just multiplication. Multiplication is like repeated addition. That is the notion of multiplication that we're going to use here. There are other ways, area of a box or something like that. They all have like different meanings for when we're teaching, like grade school children how to multiply. But for right now, we're gonna focus in on the repeated addition. So suppose I have a real number, also known as a scalar, and a vector, some vector. We're still working in the plane for now. If I wanted to multiply the number by the vector, say 3 times the vector 2 1/2, I'll get a new vector. So c times v is the vector 3 times 2 1/2. Well, if you're thinking, oh, we could just distribute or something like that, kind of actually. So what we do, take this thing, take your original vector. What does it mean to multiply it by 3? It means add it to itself 3 times, tip to tail. That's it. Now, what point? The question is, what point is this? That's what we need to ask. Obviously, the composite is the one that you get when you draw the line from the origin to the tip, the last terminal point. And sure enough, I mean, by inspection, but also by, I don't know, it's obvious, right? This is going to be the point, or the vector 6 3/2. And sure enough, what we had to do was multiply the 3 by each component. So 3 times 2 and 3 times 1/2. Also known as 6 3/2. Okay, very natural definition of multiplication. We call it scalar multiplication because vectors are a little bit more sophisticated than just numbers. And so we have different notions of multiplication that we'll be talking about. But this one is scalar multiplication, and you can take that one to the bank. So let's just do it in general like we did before. If I have c as a real number and v as a vector with components v1, v2, then the scalar product c times v is cv1, cv2, that vector. Okay, this is the definition of scalar multiplication. Now there is a special case where you take the number -1 and multiply by v. We write that as negative v. It is another version of, well, it's not another version of v. It is a new vector. What does it look like? It looks like this. Take your original vector, rotate it 180 degrees, or stretch it negatively. Okay, well, anyway. And then move out in that opposite direction. So this is negative v. It is very useful to help us define subtraction. In other words, right, if you can add and you can multiply, then you can subtract. You just multiply by -1 and then add. So u minus v is literally defined as u plus the negative of v. Just like you would have for like regular negative numbers, negative vectors. There you go. Okay, everything we've done up until now has been living in the plane. I almost tripped earlier, like at the very beginning. I moved to higher dimensions. Fortunately, everything that we've done so far was just talking about the components of the vectors, or tip to tail business in space, in geometry. Those notions generalize perfectly. So you want to add together vectors in 3-dimensional space, also known as R3. Well, all you have to do is go tip to tail. So I have U and then V, and I've tried to, draw out where they are located using just some dotted lines. If you go tip to tail, then you end up with this new vector U plus V, 1, 3, 2. And if you squint hard at this diagram, or maybe try it yourself, uh, you should be convinced. Yeah, this is very natural. Notice that R3 is the set of all ordered triplets of numbers. We can go higher, though. We can go to Rn. However, the pictures are not good. Okay, right. Just you on one level, you could just draw a bunch more axes. But because our brains can visualize this two-dimensional drawing as a three-dimensional space because our brains are very three-dimensional naturally. But my brain is not four-dimensional. And if yours is, come talk to me during office hours and we'll make a lot of money together. Okay. No, we can't really do these pictures. However, we can lean more into the algebra and just almost distill out the algebraic properties that vectors satisfy. Okay, so here we go. A vector in Rn. A vector in Rn, where n is like the number of components, that is an ordered n tuple of real numbers. Tuple, that sounds really weird, but think about it. A triple, quadruple, quintuple, sextuple, whatever. Same way we talk about octagon, hexagon, that kind of thing. And then we do n-gon. Well, here we have an n-tuple, is what it is. Okay, and most importantly, it is ordered. The order matters. Okay, tuple of real numbers. Now, I've written this as a row vector, parentheses, column vector, brackets. Again, that doesn't matter. The notation is yours. I actually will be doing parentheses and column vectors, but notice all it is just a longer ordered list. Again, geometrically, all bets are off. Now we arrive at the main dish. What are the algebraic properties of vectors in Rn? This looks intimidating. Okay. What we're going to do is I will tell you what each of these properties are. I will prove the first one. The second property has a proof in the book, which I encourage you to read and try to trace through. And the rest of the properties are left as exercises. I highly recommend that you do those exercises, especially if you plan to take higher courses in mathematics. You will be doing yourself a big favor, but it's not required work for our class. Okay, so what are these? Oh, and also, by the way, I love this theorem because it's got the fanciest words ever, and you get to pull them out at parties, and everyone thinks you're really smart. I'm kidding. Okay, anyway. So it goes like this. Start with U, V, and W, which are vectors in Rn. No tricks. And then also pretend that C and D are just scalars. So in other words, we're starting out this theorem by stating all these things up front, and then we're just going to make statements about vectors in Rn and scalars. Okay. First one, commutativity. That is, we've already seen that one. That was the case where it didn't matter if you did U plus V or V plus U. They end up getting you to the same location. So addition commutes. The next one is the associative property or associativity. If you take two different routes to get to the same location, if I go east and then north and then east again, I could have gone east and then north. Would have gotten me to the same location. Yeah? That's the idea behind associativity. The order that you add things in doesn't matter. Then we have the existence of an additive identity. This is the zero vector that we were talking about. Adding the zero vector does not change your location. Sure enough, if a vector is measuring displacement, and then so you do some displacement, and then you do zero displacement after that, where are you when you're done? Well, wherever the first one got you. Okay, great. The second one is like it. We have the additive inverse. So if you add a vector and it's negative, It's like going somewhere, like going somewhere and then coming back. Okay, okay, what is the total trip that you've taken? 0. You haven't left. Or it amounts to never having left, right? Next is distributivity. There are actually two versions of distributivity. So if I take a number and multiply by a sum of vectors, I can distribute the number over the sum, just like you can with basically every other distributive property that you've seen. But what's less obvious is if I take the sum of two numbers and multiply that sum by a vector, I can distribute the vector over the sum of the two numbers. I encourage you to try an example in like R4. Try this in R4. Just write down write down one vector in R4, so an ordered list of 4 numbers, and then pick 2 more numbers, add them together, and then multiply that sum by your vector. Then, before adding them together, multiply the vector by each of the 2 numbers separately, and then add the two resulting vectors together. You should get the same answer. Okay. The next one is another form of the associative property, which is that if you have, again, 2 numbers, you multiply them together and then multiply that product by a vector. That's the same as multiplying one number by the vector and then the next number by the vector. This one is more of a technicality, but it is a property that they obey, and it is very important for certain mathematical proofs, right? We need to appeal to this property. And then the very last one is the existence of a multiplicative identity, which is literally if you take the number 1 and multiply by a vector, think about how much that scales the vector. It's not stretching or shrinking it because all of the components are being multiplied by 1, so they're all staying the same. And so we're left with just the same vector that we started with. Okay. I want to prove for you the first one, the commutative property, so that you can see how one of these mathematical proofs go. We will be doing more proofs as the semester goes on, but for now, we're just going to do the one because it's all of the different proofs for all 8 parts of this theorem are the same up to whatever you're doing. Notice every single one of these properties is obeyed by real numbers, right? I mean, the distributive property. We learned that one in middle school, high school, something like that, right? And so we know, like, real numbers definitely satisfy these properties. So the goal is, I'll just tell you what the overarching goal is. Appeal component-wise to the corresponding property of real numbers. Okay, let's do it. We write down U plus V. Well, what is that? Well, U and V are vectors in Rn. By definition, they look like this: U1, U2, all the way up to UN. And V1, V2, all the way up to Vn. Right? This is what it means to be a vector in Rn. And now we're going to add them together. So this is, let me label this equal sign though. This is the definition of Rn that we just appealed to. Next, by the definition of vector addition, well, we add component-wise. This was our great definition. It just goes, take U1 plus V1, U2 plus V2, and so on up to un plus vn. And now, the main dish, the actual content of this theorem. Real numbers satisfy the commutative property. The commutative property of real numbers tells us that this is equal to, well, if I have u1 plus v1, whatever real number that is, it's equal to v1 plus u1. Just switch the order of addition. It'll give you the same real number, I promise. Right? v2, u2, all the way up to vn plus un. In order for this step to be false, you'd have to be able to find two real numbers whose sum changes depending on the order that you add them in. There are no real numbers that behave like that, of course, right? And so, but notice we can now go backwards. This is just v1, v2, all the way up to vn, plus u1, u2, all the way up to un. How did I know? Because that's the definition of addition of vectors. And we go to the last step, which is that we have v plus u. Because the first vector is the vector v and the second vector is the vector u by the definition of vectors in Rn, right? So we broke everything apart, appealed to whatever the corresponding property was for real numbers only. Notice we had to use that property n times, one for each of the sums that we reversed, right? And then once all the sums were reversed, we could split the vectors apart using things that we know. And the point is, okay, if it seems like this is a lot of work to just say like something obvious, the problem is the things that you know to be true for real numbers aren't necessarily true for vectors. These are new mathematical objects, and the number one advice that I can give to you coming into this linear algebra course is to know that things don't always behave the way that we expect them to. For example, I haven't told you how to multiply two vectors, but I have told you how to add them. Now, normally with real numbers, what's the big idea? We just add and multiply. But we've seen one form of multiplication that doesn't quite behave the same. The next one is even worse. We'll talk about how to multiply two vectors in a way that the output isn't even a vector, it'll be a number. And so, yeah, this is crazy. So anyway, so that is an advertisement for section 1.2. We have one last topic to cover, which is linear combinations and coordinate grids. This will be rather straightforward. So this is the last thing on the list of how do vectors behave, right? So a vector, v, is a linear combination of the other vectors v1 through vk. If you can find numbers c1 through ck, such that taking c1 times v1 plus c2 times v2, all the way up to ck plus vk, or ck times vk, take all those numbers times each of those vectors, add them all together, and you get the output, which is just the vector v. I've written that neatly in sigma notation because it's way faster and not so many dots. But the idea is, given a list of vectors, can you find a bunch of numbers called coefficients where you multiply each vector by its corresponding coefficient, add all of the new modified vectors together, and get to the vector v? That definition is a little bit dense, but let's look at an example, right? The vector 0, -3, 2 is a linear combination of the vectors 6, 1, 1, -1, 0, 2, and 3, 4, 5. And it uses these coefficients 1, 3, and -1. So what we're going to do is just blindly follow the instructions given to us. So the question is, what is the number or the vector 1 times 6, 1, 1 plus 3 times negative 1, 0, 2, minus 1 times 3, 4, 5. So what is this new vector? Well, this is just 611 plus negative 306 minus, plus, I should put a plus, negative 3, negative 4, negative 5. And then addition is component-wise. So we add the first three components together. You get a 0. Like the first component of each of these three vectors. So 6 minus 3 minus 3. Then we do 1 plus 0 minus 4, which is negative 3. And then 1 plus 6 minus 5, which is 2. Right? So it works. We just verified. We verified what we were saying. So in other words, the vector 0, negative 3, 2 is a linear combination. This is not in other words, it's the same words. It's a linear combination of 611, negative 102, and 345 with coefficients 1, 3, and negative 1. Okay, that's what it means. Notice we had to multiply each vector by the coefficient and then add the whole thing together to get this vector that we're running as a linear combination. A little bit more interesting is, what if you had this vector 1, 2, and you tried to write it as a linear combination of 1, 1 and 3, 3? Well, this is bad because, well, what do we have to do? Let's take the first, one thing we have to do is, we have to do 1 times the first one, because we need the coefficient. Well, actually, let's do it this way. Let's take any number times the first one. Doesn't matter what number. You pick. I'm calling it C, apparently. And then take any number times the second one. If you add these together, you'll get the vector, I guess, C plus 3D, C plus 3D. For real numbers, C and D. Well, notice these components match. That's bad, because, well, it's bad for our vector 1, 2, because the components of 1, 2 do not match. In other words, no matter what vector we had chosen, or what numbers we had chosen for C and D, you'll always get something that's like 5, 5, or 12, 12, or negative 3, negative 3, whatever, right? No matter, you can even choose zeros for C and D. You'll get 0, 0, right? And so no matter what you do, the first and second component of this vector matches. And so it's impossible, like, every single linear combination that you can write down of 1, 1, and 3, 3, out of all of them, none of them are this vector. And so we can't do it, right? The reason for it, by the way, here's 1, 1. Here's 3, 3. Now, anytime I multiply a number by a scalar, I am stretching that vector out in the same direction. So up to potentially having a stretch, and then doing a tip to tail situation, every single vector is going to be on the line spanned by this, in the same direction as 1, 1 and 3, 3. But let me draw for you the vector 1, 2. The point is, it is in a different direction, and there's no way to get out of this line once we're inside of it, right? And so, there's no way to make 1, 2 out of these other two vectors. This creates an interesting idea, which is that if the two vectors that we were trying to use to take a linear combination were themselves not on the same line, then we should be able to use them as like janky coordinate axes to span the entire plane, and then we should be able to access any vector. That's actually true. So let's do it real quick. This looks interesting. So first thing I want to tell you about are these symbols E1 and E2. They are vectors. For now, I will tell you their proper name. The name for these vectors are standard basis vectors of R2. We don't know what a basis is, so we won't talk about that just yet. But notice they're like really nice. They're the ones that correspond to a unit step in the x direction and a unit step in the y direction, E1 and E2. Okay, now it is not hard for us to use those two vectors to locate any vector in the plane. For example, the vector w equals 1, -4. Go over 1, go down 4. Very easy thing to locate. But, oh, and notice we can do that in terms of a linear combination. We just do 1 copy of E1 and -4 copies of E4, and then we add them together, and lo and behold, the algebra agrees with the geometry, right? But what about if I wanted to use these two other vectors, u and v? So we'll do u is equal to 1, 2, and v equals 2, 1. Okay, so I've claimed here that w is -3u plus 2v. So let's do that algebraically real quick. Algebraically, I would like to use a different color. Algebraically, -3 times 1, 2, we're just going to verify here, plus 2 times 2, 1 is -3, -6, plus 4, 2, which is 1, -4. Like that. 1, -4. Just as promised. But geometrically, think about what it means to have -3 u's and 2 v's. I don't know what these are. Okay. -3 u's, that means going 3 copies of u in the negative u direction. Well, here's the u direction. So the negative u direction is going to be down this way. Here I've got those -3 u's. Similarly, 2 v's is like, once again, I don't know what this guy is. Probably me trying to solve a different problem, but using the same graphic. Yikes. 2 v's are going to be 2 steps in the v direction. There they are. And then if you add those things together, look at where you end up. Precisely, it's like 3 negative grid lines along the v direction and 2 positive grid lines along the u u grid lines or whatever. We've written a new coordinate grid over top of our original R2, and we've used it to locate, a new vector, the vector w. Okay, so this was a lot, but this is the intro to linear algebra. What is a vector, right? So in the next video, we'll talk about what is scalar multiplication. The dot product is what we'll talk about. What does it mean to multiply 2 vectors together? I will see you in the next video.